Alright, hello, welcome back to another Mathcounts meeting. We're not gonna do warm-ups in this meeting, and we're just gonna start where we left off in the last meeting. So we're going to finish up the 1990 chapter team problems. And so we have how many triangles are in this figure. So what I would do is I would count separately the different kinds of triangles that we have. Like I would first count the smallest triangles, which would be like these 1 unit ones, and then I would count a larger, kind of lagging. Okay. Then I would count the larger triangles, which would be for the small triangles. Then I would count the largest triangles, which would be like this. Why is it okay. And it would look like this. Do you have anything to say, Bill?
Not particularly, just like you said, you should count the different sizes and also make sure that you count each one and don't overcount or undercount.
Alright, okay. My pen is like lagging. I'm not sure why.
Mm. Is it like really bad?
Here, hold on. I guess it's alright. I probably have too much stuff running in the background. Alright. So let's first count these small triangles. These would be very easy to count because they can't like overlap in any way. So you just count each of these units. So if you count them, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Wait, did I count wrong? 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6. Yeah, it should be 12. So we have 12 small triangles, and then now we need to count these slightly larger triangles. So if we just look at this big upwards triangle here, you can see that there are three of the medium-sized triangles that are going upwards. So let's just put 3 up for now. And then so same thing by symmetry with the downwards one. Now now there aren't any more. We've counted all of the medium triangles, and if you were thinking like there could be more directions than just up or down, there's actually not. So like if you thought like you can consider like the triangle like pointing this way, um and you get those medium triangles, well that's just the same ones as we did as the downwards ones. So yeah, 3 up, 3 down, that equals 6. And then we count the largest ones. There's only two of the largest ones, pretty obviously. So 12 plus 6 plus 2 is 20. Right? Okay. The height of a right circular cylinder is twice the diameter of its basis. Okay, so we have a right circular cylinder. Um, the right, so okay, a cylinder is just like this, right? And Bill, the right part is just saying like,
Yes, the right part is just saying that it is upright. So it makes
but
a
isn't a cylinder already like defined like that? Oh, or
you can
maybe it
have
could
like
be
a,
like
yeah,
you have like
skew.
slanted bases, right?
Yeah,
Um, so right, the right part just means that the height and the base is
they
with a
make a
right
right
angle.
angle.
So like your normal, yeah, your normal image of a cylinder, and so the height of it is twice the diameter of one of its bases. Okay, well, so like let's say the diameter is d, and the height is 2d. If the radius of a base is 6 centimeters, find the number of square centimeters in the lateral surface area of the cylinder. Express the answer in terms of pi. Alright, so if you want to find the lateral surface area of the cylinder, there's a formula for it. It would be pi times the diameter times the height. Um, so if you didn't know this formula, you could also kind of figure it out on your own. So if you think of the cylinder, so the lateral surface area would be this around area, right? So all the surface area of the cylinder minus the two bases, right? Because it's lateral surface area. So you can think of this area thing as like you can unravel it into a rectangle, right? And then so like the bases would have been here and here. And so like if you put it back into a cylinder, you would wrap this rectangle around the bases. But we just want to find the area of this rectangle, and that would be our lateral surface area. And so because of this, this side of the rectangle goes all the way around the circle, this would have this side of the rectangle will have to equal the circumference of the circle, which is just pi times the diameter of the circle. And this is just the height of the cylinder. So the area of this rectangle is just pi d times height. So that's how you can prove the lateral surface area formula for a cylinder. So now we just need to find it. It says the radius is 6 centimeters. So the diameter is going to be 12 centimeters. And height is 2 times the diameter, and the diameter is 12 centimeters. So the height is 24 centimeters. So now we have pi times 12 centimeters times 24 centimeters. And this is just going to be 144 times 2, which is just going to be 288 times pi centimeters squared. And it is, yeah. Oh, it actually doesn't say, oh no, it says units. Okay, anything you want to say, Bill?
Not really. Basically just if you didn't know, the lateral surface area of a um of a of something is just the surface area of the thing around it. Like for a prism, it's just the surface area without the base.
Yeah. Lateral surface area of the prism is the surface area of the prism without counting the bases. Okay, a basketball team has played 12 games and won 10 of them. If the team wins 44 and 4/9% of its remaining 18 games, what percent of its games has the team won at the end of the season? All right. So we need to count. How many wins the team got with the remaining 18 games. So if they won 44 and 4/9% of the remaining 18 games, we could just multiply those two numbers together to get how many games they won out of those 18 games. All right, so 44 and 4/9%. So we're gonna have to convert this into like a decimal or fraction or like a fraction, so that we can actually like multiply it. So there are multiple ways to do this. One way is to first convert this 44 and 4/9 part into a decimal. So if you have anything divided by 9, it's going to be that anything repeated after the decimal. So 4/9 is going to be 0.444 and so on. And then we still have the percent. And then now with this, if you have something with a percent, you can just change it into you can remove the percent by moving the decimal 2 places to the left. So then you have 0.444 repeating without the percent. And then this is just the same as 4/9, right? Yeah, because you have 0.44 and it's going on and on. Now, there are other ways to do this as well. So you could put the 44 into the fraction to make an improper fraction. That would probably take more work. So you'd have 44 times 9 plus 4 on the top, and you still have over 9%. So 44 times 9 is going to be 360 plus 36, which is 396. 396 plus 4 is going to be 400 over 9. And then to convert or to get rid of the percent for this, you can just divide by 100, right? That's the same thing as putting the decimal to 2 places to the left. And because we have 400, dividing by 100, it would cancel with the 2 zeros of the 400. And this would equal 4/9. So yeah, we get 4/9 either way. Okay, so 44 and 4/9% equals 4/9, and we can just multiply this by the 18 games they played to find how many of those 18 games that they won. And 18 over 9 is going to be 2. 4 times 2 is 8. And okay, so now let's find the total number of games that they played, which would be 12 of these and then 18 of these. So they played 30 total games. And they won 10 from there, and they won 8 from there. So they won 18 total games. And we want to find what percent of the games that the team won at the end of the season. That would just be 18 over 30. And then we can simplify this by getting rid of a 3 on both top and bottom. So then we have 6/10. Now 6/10, we want to convert this into a percent. To do that, we just multiply by 100. So that would be, 100 over 10 would be 10. 6 times 10 is 60. Oh, it's glitching out. So we have 60%. Okay, anything you want to say, Bill?
Right. So the main takeaway from this problem you should get is that if you have like if you have something repeating, then it is the number of digits that is repeating over 9 over the over like over the number of over the number of digits and have that in 9 basically. So in this case, you have one digit repeating and that is 0.444. So in this case, it was 4 and then over 9, only one 9 because it's a single digit.
Yeah. Yeah, so like 1/9 is 0.1111, so on. 2/9 is 0.222, so on, and yeah, so on. So yeah. All right. If 235 feet of fence and a 5-foot gate are used to construct a rectangular dog pen, find the maximum area in square feet that can be enclosed. A 5-foot gate. What does that mean? Does it just like add on to the feet of fence?
I'm assuming yes. It's
Okay,
adding on to the fence because the gate
okay.
is not a fence.
All right, all right. So 235 feet, we have a fence. We have 5 foot of gate. So in total, all of our stuff, we have 240 feet. And I guess for a gate, you have to keep it in a line. But because it's so small, we like barely have to consider that. Basically, it's just you can't have a side that's smaller than. Actually, no. Actually, that doesn't even matter. Okay, so basically, we have 240 feet of um like 240 feet of fence basically, and we want to use that to enclose an area, and we want to maximize that area. So if you didn't already know, if you have a set amount of length of a rectangle and you want to maximize the area of that rectangle, the best proportion of size to use is a square. So you want to put it into a square. Now, why is a square the best area to perimeter ratio? Well, I mean, you can think about it with limiting cases, right? If you make it as non-square as possible, where you have very long sides to very short sides, this is not good at all because you're using a lot of length to close barely any area. So that's why you want a square where you have the where the sides are the same length. So yeah, now we just put this onto here. This is going to equal the perimeter of the square. And so because the sides of the squares are equal, the side of the square is just going to be the perimeter over 4 or 60 feet. And we just need to find the area of the square, so 3,600 feet squared. All right, yeah, so the main takeaway from this problem is if you want to maximize the area of a rectangle and you have some set amount of perimeter length, then you always want to put it into a square. Now, if you had no constraint on the shape being a square or a rectangle, I mean, then a square is actually not the best shape. Then you would want to construct a circle, which is a little bit better than a square. So yeah, so if you have a set amount of perimeter and you want to enclose the greatest amount of area, and it doesn't care like what kind of shape you use, then use a circle. Okay. And in 3D, if you had like a set amount of surface area, and you wanted to enclose the most amount of volume, then you would use a sphere. I can't really. Okay, yeah, a sphere like this.
Yeah.
Or actually, yeah. And if it said that you had to use a rectangular prism, then use a cube. All right. Anything you want to add, Bill?
Basically, just for this, if you're given a set amount of perimeter or surface area, the largest area or volume you can get out of it is whatever is however close to a circle or sphere. The the closer you get to a circle or sphere, the greater the area or volume will be.
Yeah, yeah, yeah. All right. So now that was all the 1990 chapter problems. Um, So should we move on to state or next year's chapter?
Let's let's do state.
All right, let's try some harder state problems. Okay, we actually need this stuff. Okay. All right, so we're gonna start with sprint. Susie's dog. Susie, maybe we could do like this. There you go. All right. Susie's dog eats 2.5 cups of dog food per day. If the dog food weighs 4 ounces per cup, how many days can Susie feed her dog with a 40-pound bag? All right, so she has 40 pounds of dog food, and each cup of dog food weighs 4 ounces. All right, so we have 4 ounces, and we want to convert this into pounds. You have 16 ounces per pound. Ounces cancel, then 4 over 16 is 1/4 pounds. So every 1/4 pounds, every 1/4 pounds of dog food, there are a cup of dog food. Every 1/4 pounds of dog food, there's a cup of dog food. All right, so we have 40 pounds of dog food, and we want to convert this into cups, right? And so we can just divide it by the 1/4. This is like 1/4 pounds per cup, right? And we have pounds here, and then this is pounds per cup. So your units work out. So it's going to be cup. And this is, so if you're dividing by fraction, you're just multiplying by its reciprocal, right? Reciprocal of 1/4 is 4 over 1 is 4. So that's 40 times 4 or 160. So we have 160 cups of dog food. And the dog eats 2.5 cups of dog food per day. We want to know how many days she can feed, right? So we just divide it by 2.5. 2.5 cup per day. Cups per day. Right. So if we divide cups by cups per day, the units work out. We get what we want, which is days. And 160 over a 2.5. Okay, so we can convert 2.5 to 5 halves, right? That's just 2 times 2, 4 plus 1. And then again, if you're dividing by fraction, you multiply by its reciprocal. So we have 260 times 2/5. We should divide by this 5 first, which will give us 32. And 32 times 2 is 64. So that's our answer, 64 days. How many 36 are in 83 and 1/3%? Okay, so if it's asking how many something, if it says how many X are in Y, then we do the operation Y over X, right? Like if it asked how many 2's are in 4, well then it would be 4 over 2 or 2, right? So 2 2's are in 4, so it is Y over X. So in this case, it would be 83 and 1/3% over 36. 36. 36
130.
is that, right?
I don't think so. If it's asking for 36, there wouldn't be a dash there. there wouldn't be a hyphen between the 30 and the 6. So I'm thinking they're asking about
How
136.
many 36? How
Yeah,
many 30? Wait, what?
I think they're asking for how many 136 are in that.
How many what?
How many 136?
136?
Yes.
What do you mean with the 1?
Like 1 over 36.
1 over 36?
Yes. If it's 30 over 6, there wouldn't be a hyphen
Oh.
between the 30 and the 6.
So if it was saying 36, that would be 30. That would be 30. That would be 36s, right? Oh
Yes.
my pen is glitching out. But it's with a th, so it's not that.
Well, no, if it was saying 30 over 6, it'll still have the th, but not the hyphen, not the dash
No,
between the
I'm
30.
saying it's not 36.
You're
What?
saying it's not 36?
I'm saying it's not 36, but not 1 over 36.
Okay, okay, yeah.
And then what are you saying? So if they said if they meant 30 over 6, what do you think they would say?
If they meant 30 over 6, it will be 30 space 6. There wouldn't be a hyphen there.
Okay. Okay, I am good with that. Okay. So um okay, yeah. So Bill's saying that if they meant 30 over 6, that they would say 36, and because there's a hyphen, they mean 1 over 36. Okay. So this is actually our expression right here. And so what are we going to do? So if you're dividing by a fraction, you're multiplying by its reciprocal. 1 over 36 reciprocal is just 36. So that's just 83 and 1/3% times 36. And we had to convert this into not a percent, right? And again, you can do this in multiple ways. Okay, let's do the convert into fraction way. So converting this into a fraction, it's going to be 83 times 3 plus 1, which is going to be 249 plus 1. So that's 250 over 3% times 36. Now we have to convert this out of a percent. So you just divide by 100. So so now we have 250 over 300 times 36. And we can cancel these zeros out and cancel out a 5 from top and bottom. And we can cancel out a 6 from both of these. So it's 5 times 6, or 30. Wait, it says 30 or 36?
Yes, because in this case, we're counting how many 36 there are. So, we have 30
Oh,
36.
okay. Oh, okay, I get it. Okay. Find the result in decimal form when 1.25% of 1,000 is added to 12.5% of 100, and that sum is subtracted from 125% of 10. Okay. Whenever you have percent of something, that just means you multiply them. So what we're trying to find is 1.25% times 1,000 plus 12.5% of 100, subtracted from 125% of 10. Now, so these things actually equal the same thing, right? Because each of these times you're dividing this by 10, right? But you're multiplying the percentage by
Hey
10.
Austin.
So those would cancel out. Well, yeah.
It's saying that that sum is subtracted from 125% of 10. So it should be 125% times 10 minus the other stuff.
Wait, what?
It is saying and that sum is subtracted from 125% of 10.
Oh, okay. It should be the other way around, you
Yes, it
mean?
should be the other way around. And
Yeah,
also
yeah.
the back is in a parentheses.
Wait, what?
The back, yeah, okay. Yeah, you're fine.
Oh. Okay, so it's saying, okay, so you have the sum of 1.25% of 1,000 and 12.5% of 100, and it's subtracted from that. So it would be here. If it said it's subtracted by that, then it would be like that. Okay, so this is what we actually have. And something you can notice is again that all of these things are the same, right? Because it's like you're multiplying the percentage or dividing by 10, and you're doing the opposite thing with with the other thing. Like to get from this to that, you multiply the percentage by 10 to get 12.5%, and you divide this by 10 to get 100. And because you're multiplying and dividing by 10 in the same thing, you're not changing it at all. Okay, so if all of these are the same thing, then we can just like cancel one of these out, right? Because this is positive, this is negative, so they cancel. Now this is still going to be negative, right? Because it's in the parentheses. So now our entire value is just 12.5% of 100. So again, you want to get out of this percentage. You can do this in a lot of ways. Um, you can move the decimal place back by 2 to get 1.25 times 100 with the negative, and you can recognize that 0.125 is just 1/8. If you don't recognize that, you can just put 125 over 1,000 and simplify that. All right, so now we have negative 1/8 times 100, and you can cancel out a 4 from both of them. So now we have negative 25 halves, but it says find the result in decimal form, right? So don't forget to convert this into a decimal, which would just be negative 12.5 if you just divide that out. So yeah, that's our answer. Okay. Evaluate this expression if x and y and z equals that stuff. And we have that. Okay, so this is just a simple plug-in thing, right? So I'm not going to spend much time on this. So x equals -3, right? So -3 times -12 is going to be positive 36, right? And x minus y, so it's going to be -3 minus 5. That's -8 times z is going to be -8 times -2, 16 plus 36. And then we have z minus 5 times that. 16 plus 36 is going to be 52 times 5. And you subtract it from z, which is -2. 5 times 52 is 260. We have -2 minus 260, so -262. All right. Okay, what is the greatest common factor of A and B? Oh, if the greatest common factor of A and B is 1, what is the least common multiple of 12a squared b and 30ab squared? Okay, I think there's a really cheesy way to do this. So if it just says like if the greatest common factor of A and B is 1, you can assume values of A and B where it it I can't find the word, like where it, oh my god,
Where they're relatively prime to each other, or like
no, I
where the numbers are
okay,
equal to or equal
you can just assume the values of A and B to where it makes that statement true, and then you can do the rest of it. That's just like a cheesy way, and you can get away with that on math counts, because I mean they just want you to find the value, right? But if it was on like the USMO, and it wanted you to prove that for all of A and B where GCF is 1, that the LCM of that stuff is something, then you'd have to write a full proof, and you can't assume like just a few values of A and B and plugging them in, right? But because it's math counts, they just want you to find one value. You can just assume values of A and B. Oh, okay, wait, they actually want you to yeah, okay. So what you should do, actually, what would you do here, Bill? I think what I would do is I would test two values of A and B,
so
like two sets of A and B, and if they equaled each other, I think I would just write that down.
well so for this one, because you're working with, it's not the 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 condition that if the greatest common factor of A and B is 1, that is just saying that A and B are relatively prime to each other. And so in this case, I feel like you could just work with just the letters and don't worry about having to substitute in actual numbers, because it wants the final answer in the form of A and B. So in this case, I feel like you
How do
could.
you know that how do you know that it wants like something in A and B and not like a number?
Well, it's going to have to be an A and B because you can't get a number.
All right, sure.
You
So
can't.
yeah,
You can't. You're not going to be able to just get a number answer for this. It's going to have to be in terms of A and B.
okay. Yeah, so what Bill is saying is because like this LCM of this stuff is going to change as you change A and B. You can't just have one value for it. So we're gonna have to work out the we're gonna have to work it out with the letters. So if you're saying GCF of two numbers is equal to 1, you're just saying that they're relatively prime. Um, and when you say A and B are relatively prime, that just means that they don't share any common factor. Um, so like 8 and 4 would not be relatively prime because they are both divisible by 2, but 9 and 8 would be relatively prime. Even though these numbers themselves aren't prime, they don't share any common factors, so then they're relatively prime. So again, if GCF of two numbers is equal to 1, that just means that they're relatively prime. Okay, so now we want to find the least common multiple of 12a squared b and 30ab squared. So again, I think we said this in the last meeting. If you have the least common multiple of two numbers, you want to take, so if you have their prime factorizations, you want to take the largest power of the you want to take the largest power for each of the primes and have that in the LCM. So like if you had the least common multiple of 2 squared, 3 squared, and 2 cubed 3, you look at each of the primes, the 2, and you find the greatest power. The greatest power of 2 in both these numbers is 3. So we're gonna have to have 2 cubed in our least common multiple, and then we look at 3. Its highest power is 3 squared. So we're gonna have that in our least common multiple. So, I mean, should we do it that way in here though?
I don't see why not.
So you can think of the same thing, but you don't have to use like so like you can treat actually sure, let's do it like that way. Okay, so prime factorization of 12 is just going to be 2 squared 3, and 30 is just going to be 235. All right, and then we're gonna have a squared b and ab squared, but we don't know what a and b are gonna be. So we know we have to have at least 2 squared, 3, and 5 because these already have it. But if A and B have any more of these, then we'd have to change that. Bill?
I think it's safe to assume just out of the bat that we can just treat A and B as relatively prime to as mutually relatively prime and also relatively prime to 12 and 30. I think it's safe to assume that because at this level I wouldn't think that they would
Yeah,
expect you to consider that.
No, I was gonna say I don't agree with their solution, their answer, unless A and B had to be relatively prime to 12 and 30 as well.
Yes, but I just think at this level they're not going to expect anyone to be considering that. The case where A or B may share a factor with
No, well, I mean that's
12 and 30.
I think they made a mistake on this problem. I don't think I definitely think they should say like A and B are relatively prime to 12 and 30. Like if not, then like I don't know, like you can't do it
Yes,
like that.
I understand what you're saying.
Yeah. Okay, but yeah, so what would you do if you were faced this on the actual test?
So
I guess so because it I don't know, like at this point I guess you should just skip it. So if you find actually okay, so if you're working through this on the test and you got to this point and you're like well, you know, we don't know that A and B is relatively prime to that stuff, so it changes. The stuff, the formula changes as you vary A and B. Then you should probably see if you can assume anything like where they made a mistake that they forgot to specify something, and then that would make it work out. So like assuming that A and B would be relatively prime to 12 and 30. but you shouldn't spend like too much time thinking about like, oh, what have they made a mistake on? Like if um like if you're spending too much time on it, just skip it. Yeah.
Yes, so something you can do if it's for a problem like this, something you can do is think about what would the person writing the test be thinking, right? Because if the test writer probably is not going to expect you to consider the possibility of A or B sharing a factor with 12 or 30. So,
Or yeah, you can think that, but also don't spend too much time thinking
yes.
about that. You also want to get to the other problems. But let me briefly explain on why their solution of 60a squared b squared would not work if a and b um were not relatively prime to 2, 3, and 5. 2 squared, 3, and 5. So if A and B were relatively prime to these, meaning that they don't have 2 squared, or meaning that they don't have 2, 3, or 5 at all, then it would be equal to this. Why? Because you're going to have 2 squared, 3, and 5 from this, and then we know A squared, or we know A and B don't have any of these, right? And we know that they are relatively prime in themselves, right? So they're going to contain some primes. So we're going to have some primes from A, some primes from A, and we're going to have some primes from B. Now, all of these primes are not going to be equal at all because A is relatively prime to B, and right now we're saying that A and B are also relatively prime to 2, 3, and 5. So they're not going to have any of those. So because these are new primes, we're going to include all of these new primes into our least common multiple. So that would mean having the highest power of A, which is A squared, having the highest power of B, which is B squared. Now, if they aren't relatively prime, this is not the case because, like, let's say A contained a 2 in its prime factorization, then A squared would have 2 squared, right? Now, you shouldn't be counting it A squared in your thing, right? Because then you're counting 2 squared from A squared and you're counting a 2 squared from 60. But remember that, actually, no. Because they're together, that would work out. But let's say B had the 2. If B's prime factorization had a 2, then B squared's prime factorization would have 2 squared, right? Now then, Then, then this prime factorization would be incorrect, right? Because on this side, you'd have 2 times 2 squared, which is 2 cubed. And on this side, you would have 2 cubed. And in this, you're just supposed to have 2 cubed, right? That's your highest power of 2 in both of these. But you're counting a 2 squared from 60. You're counting another 2 squared from B squared. So then you're counting 2 to the 4th, but you're only supposed to count 2 cubed. So yeah, that would not work out, right? So again, if they were not restricted to being relatively prime to 2, 3, and 5, then it would have to vary. The formula would have to vary as you vary A and B. Okay, but now let's assume that A and B are relatively prime to 12 and 30, and that would make everything go in one formula. So again, if they are relatively prime to 2 squared, 3, and 5, they're not going to contain any of the factors. If they don't contain any of the factors, we have to include all of it. We have to include all of it into our least common multiple, right? So let's go ahead and put 2 squared, 3, and 5 into our least common multiple. If you multiply that out, you'll get 60. And so we can treat A and B like if they were primes, and then we just look at which one has the like greatest power of A and B and stuff. And why we can do that is because they're relatively prime. It's just like if A had like 5 and no, not 5. Like if A had 7 and 11, then this side would have 7 squared, 11 squared, right? And this side would just have 7 and 11. And because this is A squared, you want to count A squared and not A into a least common multiple. So yeah, you have A squared. Yeah, you have B squared.